to everyone. Thank you for joining this webinar. This webinar is part of the CHIP Think Tank webinar series. The CHIP Think Tank is actually a series of webinars brought to you by the aCCCess project. The objective is to bring insights and reflections on the semiconductor industry from European opinion leaders. And all the previous sessions are available. They're available from the aCCCess project YouTube channel. You can have a direct access to the YouTube channel thanks to the QR code that you have here on the right of the screen. And actually, there's a CHIP think tank, but also some insights on the technology offers from the competence centers. And very soon, we will also start a new series about the training offered by the competence centers. So a little bit of housekeeping. This webinar is an interactive discussion. So if you have any comment during the presentations or if you have any questions, you can use this chat, or you can enter your questions here on just on the right of the chat. And we will have this, I will take those questions one by one during the Q&A session. So my name is Régis Hamelin. I'm CTO of Blue Morpho, and I'm the coordinator of aCCCCess. And today's topic is building the materials platform for the future of integrated photonics. And I have the great pleasure today to welcome Jean-Louis Guyot, who is CTO at Rieber. Good afternoon, Jean-Louis. How are you doing?
I'm fine. I'm fine. Thank you, really, for you to give me the chance to speak with your audience. It will be a great pleasure for me, and also to interact with all your participants. Thank you very much for aCCCCess.
Yeah, thank you very much, Jean-Louis. We have indeed a nice crowd joining us today. So a few words about aCCCCess. We are actually a European project. Blue Morpho, my company, the company I'm working for, is a coordinator, and we have CNSC from Czech Republic, MESAP from Italy, Minalogic in France, Silicon Alps and in Austria, Silicon Saxony, and VDI from Germany, who are full participants of this action. You have the list of associated partners. And we also work with the support of the industry associations, ANAS, EPOS, and DeSci. In fact, we are coordinating the network of CHIPS competence centers. There are in total 30 competence centers which have been launched. And our job is to make them work as a network and facilitate the access to the pilot lines. You have the whole list on the right. And very soon we have newcomers from the quantum pilot lines, and also the design platform Euros CDP. So actually, there are three things that the competence centers are doing. First, they provide access to technology, they provide access to training, and also we facilitate the access to financial investors for startups. And actually, the technology focus area breakdown among the competence centers is listed here. And you see that silicon photonics, the topics of today, and photonic integrated circuit is probably one of the most represented technology offer among the competence centers. This is a very hot topic today, and I'm really pleased to talk about this topic today. If you want to know more about the technology offers and the training programs which are offered by the competence centers, I invite you to connect on our website, aCCCCess.eu, 3 Cs for CHIPS competence centers in aCCCCess.eu. And you will find two very new features on the website. The first one on the left, represented on the left, is a chatbot that will help you to identify your technical partners. So interacting with this chatbot, you will find where are, for example, the silicon photonics, the people who are working on silicon photonics in Europe. And if you need for your career to find a training program or for your employees, you will see also what are the training offers which are today distributed by the competence centers. So these elements are a work in progress, so it's always evolving. So make sure that you visit our website from time to time to see every novelties. A few information as well. On September, on 7 and 8, in Finland, at the Dipoli Conference Center in Espoo, there will be the second edition of the Nordic Chip Summit, which is organized by the Finnish Competence Center, FIC. And also, FAMES will host a workshop, a joint workshop with CINANO, the CINANO Institute. It will take place at the ESERC conference on September 7th in Spain. So you have the choice between Finland and Spain. Either you're interested into the pilot line or you want to interact with the Nordic ecosystem. Another interesting event, I will be a panelist, so we'll have the opportunity to meet, and you will also meet the other partners of Access at the first conference. It will be in Berlin at the end of September, and it's co-organized by the FMD and the Apex pilot line on advanced packaging. So let's interact. I would like to know a little bit more about you and where you are coming from. So I'm launching a poll at the moment. I'm asking you if in the audience you are more a small business, a mid-cap, a large company, research organization, or a competence center. And I will let a few moments for you to fill in this poll. And while you are filling this poll, Jean-Louis, welcome again. Thank you again for being with us. I would like to start this interaction with a little bit more information about you. Who are you? Where are you coming from? And how did you become, what is your background? How do you become the CTO of Ribert today?
Okay, then come on. I'm Belgian. I'm coming from the south of Belgium, the French parts. I do my study in physics, okay, at the University of Namur. I do also my PhD there until '96, where I move to join the industry. And I joined in '96 the Central Research Laboratory of Thomson, which becomes later on Thales, okay, now well known as Thales TRT. Okay, thus at Thales, I was working on a different kind of device, specifically lasers, power lasers, in fact, HBT, and also some photodetectors at that time. In the end of the 19th, I moved to Pico Giga, which was the only AP house in Europe. Pico Giga was making the epitaxy mainly on gallium arsenide based device. On gallium arsenide, was only the epitaxy. This is really my core knowledge is epitaxy and device. Okay, and thus I stayed there maybe 5 years and so on. And after I moved to a small company called Addon, where which was a company selling components for let's say for MB customers. At that time, I really want to make business development, and I start approaching with the technology developed by Addon the industry of organic light emitting diodes. Okay. Okay, just because it was an emerging. Now it's it's well known because everyone has a full television made of OLED. Okay, thus in 2007, 2008, we have been bought by Ribert. Okay, due to that diversification, we continue diversification at the early beginning in the SIGS industry, thus photovoltaic panel based on thin films, copper, indium, gallium, selenide. After Ribert offered me, of course, to continue this business development in components and service. And in 2015, they asked me to become the CTO of Ribert due to that entrepreneurship I have developed in the past. Okay.
Mm.
Thus,
Yeah,
I
very
become
interesting.
since then I'm the CTO of River.
And today we're going to talk more about a specific project within Reber, which is connected to photonics.
Yes.
So, what was your personal drive to get involved into this project?
Yes. First of all, joining a SME. Thus, I start from TRT, which is a very big group. Okay, come a well-known group, and after I join SME. Why? Because when you join SME, you have the possibility to do something, not only to push the wagon, but only to create new roads. And this is exactly where I am. However, the counterpart is when you are a SME, it's like a driving a bicycle. Okay, if you don't pedal, okay, you fall. Okay, thus this is the life of a SME. You always need to be entrepreneurship, look what's going on, take risk also, and this is exactly my DNA. And the project we will discuss today is part of that.
Okay, very interesting. Yeah. So, in fact, an SME is for you an opportunity to take risks.
Yes,
So
to take
let's
risk.
talk. Let's talk a little bit more about Riber. I'm going to make you presenter. You're going to be able to share your screen, and then we can move to. You have prepared a presentation for us about Riber and about this specific project around the ROSI equipment, which is a new machine, and why you want to use it for BTO. So you should be able to share your screen now.
Ah,
Yes, we see two screens actually.
yes. This is it, does can you switch
Uh,
off the
We
maybe
see
I
two.
need to redo it.
Yeah, we see two screens. You have to share only one screen, the
Yes,
second screen.
but I don't know how to do that. Okay, it was working.
Yeah, yeah. If you
Maybe we
switch,
can do that like this.
I will. I think I can. I can share my screen again because here it's not. I will. I will. I have your slides. If you don't mind, I can
No,
simply.
I'm really sorry,
Okay,
but
no
it was
problem.
working.
Yeah, yeah, it was working for just for the audience. We just tried
Yes,
it before,
yes,
and it was
as
perfectly
usual,
working.
as usual.
That's a demo effect. All right, so let's see if it's still working on my side. So I'm sharing now your presentation, and I'm switching to the presentation mode, and now you should see the whole screen.
Yes, thus Riber and the photonic integrated circuits. This is, I will not really speak about Riber. I will mainly speak about our vision and what we are doing now. Okay, thus maybe for reminding slightly what is molecular beam epitaxy. Molecular beam epitaxy is a very old techniques based on vacuum evaporation. Okay, thus those machine, the molecular beam epitaxy, and there is epitaxy, and epitaxy is the growth of synthetic crystal on a given crystal. Okay, thus our DNA at Reber is really the 3-5 semiconductors. Thus the 3-5, I put here the Mendelevium table. Okay, on one side you have the
No
three
problem.
elements, maybe a little bit before. Okay,
Mm.
you have the three elements with the aluminum, gallium, and indium, and you have the five element phosphorus, arsenic, antimonite, nitride. Mixing all those materials together and so on, bring new crystals you are able to grow on different substrate. Maybe we can move to the next
Mhm.
slide.
So here in this particular, so we can see that we can have gallium arsenide, gallium indium arsenide, and also
Exactly.
duo indium phosphide. So all the combinations are possible.
Yeah.
And for BTO, so how does it work here? Because
And
um,
for the BTO, this will be the next machine. Of course, BTO is a material you are able to grow epitaxially on silicon. Okay,
mhm,
because this is the first things. However, for the grow of oxides on silicon, you have to have a seed layer, which
mhm,
is mainly based of strontium oxide. okay,
Okay.
on silicon. Thus,
All right.
and the strontium, the barium are evaporated under vacuum and so on, while the titanium is evaporated through EGAN. Okay,
Okay.
oxygen is bring into the machine as molecular source or atomic source.
Atomic
Okay,
source.
using
Okay.
plasma source. Okay.
All right. Okay. Let's go on
Okay,
with the 3.5.
this is just to explain the 3.5 here. The 3.5 is, you see in the line you have gallium arsenide, indium phosphide, gallium antimonide are the main substrate you can buy, and on that substrate you are able to grow with different elements like gallium, aluminum antimonide, or using indium arsenide and so on. Different kind of semiconductors, epitaxy on the substrate. And with this, those stacks, you are able, of course, to build a specific stack for reaching, for making, for example, laser photodetector, but also some kinds of electronics. Thus, this is really the DNA of Friber. Okay, lasers emitter, making laser emitter at the proper wavelength to have a function in, for example, PIC industry. One of the for the PIC industry, you see here the indium phosphide. Thus, mixing gallium, indium, arsenic, and phosphide, you are able to reach wavelengths in the mid-infrared, like for example 1.3 micron emitter, so 1.55 micron. Why those two wavelengths? This is because this is the low loss window you have in optical fibers. Okay, and this is such kind of thing. Of course, this is 3.5 semiconductors. Thus, it needs to be grown on gallium arsenide. Cannot be grown yet on silicon. And when we are speaking about PIC, okay, this is photonic integrated circuit. Maybe we can move to the next slides. Okay, going no, yes, okay. Thus, let's not come on the 3.5 semiconductors. Friber has started since the beginning, the end of the 70s by building R&D machines. Okay, and we have started in the mid 19 to build the biggest machine, the larger machine, the mass production machines. So far, now we have the smallest R&D tools up to the largest production machines, okay, to serve the 3.5 semiconductor. The next step for us is keeping the DNA of molecular beam epitaxy, but to serve the epitaxy on silicon. And one of the material we have choose several years ago, or 2 or 3 years ago, was barium titanium oxide growth on silicon 300 millimeter. Maybe we can move to the next slides. Okay, thus the next slide is our prototype machine, ROSY machine, to grow this new material, new oxide, functional oxide materials on 300 silicon industry. Next slide, maybe. Uh, okay, thus why to choose the barium titanium oxide? Thus the barium titanium oxide has a ferroelectric behavior at room temperature. Okay, thus when you apply to this material an electric field by putting two contacts aside, you you have the chance to control the index of refraction. But if you control the index of refraction of the material, if you have light going through the BTO or beneath the BTO into a waveguide based off silicon nitride, you are able to modulate the light. Okay, thus the BTO is a modulator. Okay, this is the main properties which can cover the different field here. Datacom is obvious, okay, because you need to have transceiver, thus putting light into optical fiber, which are modulated, being able to demodulate and so on. Telecom is long haul, okay. For computing also, I don't speak about quantum computing here. I think I say that this is optical computing, Okay, just to make optical computing, you need to have light and to be able to manipulate the light, multiply a matrix, and so on. But a phase, a modulator is a phase change, a phase separator, a phase change. Okay, thus if you have a complex number and you are able to change its phase, you can have all the function for computing. There is also the sensing, because if you are able to change the let's say the phase of the light, okay, you can steer the light purely electronically. Okay, like in the past, we do the same with radar. Okay, with radar, with array of silicon carbide based antenna, you are able to scan without mechanical movement. Okay, because this is company like are working on this. And finally, and more surprisingly, there is also for the quantum computing. You know that for quantum computing, either you can choose the road for uh, let's say like electronics road, and but there is also optical road. Thus each qubit is made of a single photons, which needs to be manipulated with low loss, okay, and not on a very big let's say a circuit, okay, and this is done, at least some of the company, the leading company are choosing BTO on silicon to handle and to manipulate the single photon. This company is, for example, the US company like PsiQuantum. Uh, more close to us is Candela. Candela is also making single photons and manipulate the light through PIC circuit. Okay.
Quick question on the top right figure. You show, I'm coming from material science, as you know, so
Okay.
I'm always interesting to understand. You show various crystalline configurations for the
Yeah.
material, but the temperature chart goes from minus 90 to plus 120.
Exactly.
Can you
Yeah.
explain that? Because in
That's
MBE, you will always be in high temperature, right? Or
exactly. Thus, when you start growing, you need to bring power, come on, energy to the atoms to arrange, to build the crystal and so on. So as that, you are at high temperature. Thus, you will grow the material at a temperature between 300 degree to 650 degree. At that time, you have the material in cubic phase. You know, this is the paraelectric because you are above the Curie temperature.
okay.
However, when you cool down the material just to extract it from the grow chamber, you will have a phase change, which occur usually at higher temperature because we are building thin films, BTO, and it becomes tetragonal. Tetragonal means that, you know, in the cubic phase, you have the central atom, which is a titanium atom. Okay,
Mm,
because when it becomes tetragonal, the titanium moves up or down or aside, okay, building a permanent electric field. And this phenomenon, the tetragonal phase, makes this material ferroelectric, and with this remarkable properties. Okay, thus the job of the machine and of the grow is to force the material to become tetragonal with the proper orientation. Okay, thus I told you that you can move the titanium atom from the top to the bottom. Thus, it will mean that you will have a polarization which is perpendicular to the substrate. Okay, this is one phase. But you can also, and for peak industry, you need to have the electric field in the plane, and this is mainly the management of the stress during the grow. Okay,
mm.
you are being able. Thus, even if you have three atoms, barium, titanium oxide, you have different kind of recipe to make different kind of BTO based on what the designer of the circuit will request.
Okay. So
Okay.
let's move to the application.
Yes. Okay. Thus, for Ribert, why to enter into oxide? Of course, going from 3.5, who is a family of material who can emit light or detect light, and moving to oxides. Okay, thus let's look at photonic integrated circuit. We see that here is a let's say an artistic drawing, come on. But in fact you have the bottom plate, which is the really the PIC circuit made of silicon nitride. You have the contact. You may have also CMOS like come on, electronics in beneath and so on. But to have a PIC circuit, you need to have light. Thus, you need to have lasers which are coupled to the silicon circuit. You need to have detectors which are coupled. But in the lasers, we have already the platform to grow the lasers. And on for the photodetector, we have also the platform to grow the photodetector. This is what I show at the early beginning. For ROSI, for example, here, thus ROSI will be dedicated only to grow a material, barium titanium oxide on silicon, so as that it can be integrated by wafer bonding on PIC circuit from the silicon industry. And ROSI will only bring new material, barium titanium oxide, for making electro-optical modulators. An electro-optical modulator is simple. You have an electrical signal coming from, for example, your CMOS circuit and so on, and you transform this signal, okay, 101010, into light, no light, light, no light, light, no light. There is different architecture you can see here, Mach Zehnder, come on, ring, or a simple diffusor. Okay, this is the coherence of the BTO for Ribert.
And this is the development
Yes,
roadmap.
and this is the project. Thus, the ROSI project, which is, you can see that in 2026 we hook up our first ROSI 1.1 in Denmark. Okay, thus this is a collaboration lasting 3 years between Ribert and Denmark. Okay, where Ribert people are running the machine to grow the STO on silicon and the BTO on silicon. The target of that program, this is the POIM program, is really focus on quantum computing. Thus, research on the best material to manipulate single photon emitters.
Okay.
The technology of ROSI is not coming from nowhere. In fact, it's coming from you see the drawing here is our first oxide machine, which has been developed in the framework of a European project called INVEST in 2003. Okay, in 2003 with IBM Zurich. Okay, they use that platform, oxide platform, which were able to grow oxide materials on 200 millimeter. At that time, what kind of oxide? They don't know. Okay, it was not speaking about barium titanium oxide. You know, at that time it was mainly high dielectric thin films, just come on to move the CMOS industry forward. Okay, because this machine in 2007 has been displaced and moved to IMEC. Okay, thus we work with IMEC to hook up that machine, and IMEC start studying different kind of oxide and also the BTU oxide. And in 2020, okay, we start developing the ROSI 1.1 machine. Why? Because we had several demand, okay, from Intel just to have epitaxial oxide on silicon to make with high dielectric constant, but also some company like PsiQuantum or Lumiphase, which are two startups, think to use the properties, the Pockle effect of the BTO, just to build the next generation transceivers. Okay, because this is
Just want
yes,
to stress that you mentioned a project called POEM.
yes,
It's actually there's a competence center in Portugal which names is POEMS with an S at the end.
yes.
So I just want to stress that there's no connection between this project, which is a different
No,
project, and the
there
company.
is no connection, and I didn't know that. Okay,
Right.
no, come on. But there is also a US company called Poem.
Mm. All right.
in the big industry. So
It's a good name. It's a good
yeah,
name.
it looks like okay. No. That's in Denmark. All the material we are producing, the environment of the Rosie in Denmark, to be honest, is academic environment. Okay, thus this machine will produce wafer and components mainly for to serve the program poem. We may be able to get some samples for others, but this is not the goal. Okay, and this is why we move next. The next step for us is to build a new Rosie 2 machine, which is a larger machine with two reactors around a cluster tools,
Mhm.
and to install that platform in France. Okay, and this platform will be also managed by Reaper people, but will be more open. Thus, for a research program or a development program, mainly to bring TRL4 to TRL6 or TRL6 to TRL9. This is the platform for making industrial sampling of those materials on 300 millimeter machine. Okay.
All right.
Okay. Thus, this is this platform. This is really ambitious because the platform is under construction and will be hooked up in Q1 2027. Thus,
That's
the
very
first AP
nice.
wafer will start from that platform will start by Q2 2027. Of course,
And
this platform will
physically, you said it was in France, but where in France will it be?
in probably this not yet decided, as I cannot
Okay.
disclose that point.
All right.
Okay, but it's close to where we want really this platform to be close to industrial environment. We
All
don't
right.
want to hook that machine to let's say a research environment. Okay, thus here is a kind of resume of the sampling roadmap. Okay, of course, we have the poem line dedicated for quantum computing. We will be able to make some few sample, okay, to serve the community. Okay, but first of all, the samples, there is no feedback loop. Thus, you will have the samples we produce in the framework of poem. Thus, we cannot work in closed loop way just to improve, for example, circuitry and so on. Okay,
Mhm.
and a poem dedicated in this time for industrial sampling. Okay, thus to this is open to everyone who have idea to use BTU on silicon or STU on silicon and so on.
Okay. Yeah,
But
that's your conclusion.
yes,
Um, I suggest that we can you wrap up the presentation so that we can move to the discussion phase?
you have the end of the
Yeah.
presentation.
Here is it.
Okay.
So here we have
Yes,
all the
of
different
course, we
equipment.
start with Rosie, which is epitaxy on silicon, but there is also other uh, uh, um, other topics, like for example, Soitec has developed a substrate which is called InPosi. Okay, thus this is indium phosphide thin film from silicon. Okay, thus this machines, thus the indium phosphide is no more indium phosphide a substrate, but is a thin indium phosphide bound directly on silicon. Thus the silicon is a kind of model. Thus Sophia machine will be able to handle those 300 millimeter indium phosphide and grow indium phosphide based device on that machine. Thus, this is maybe now pure science fiction, even if there is very interesting work which has been done in Move to Terra's European project, where they work on next generation HBT on silicon. Okay, we're using this InPosi substrates and so on. Okay, thus this will be next production machines to produce such kind of epitaxy directly on silicon.
All right. Okay, thank you very much for the presentation. I suggest we move now to the more discussion phase. So don't hesitate in the audience if you have any questions or remarks. Don't hesitate to use the chat and ask your most difficult questions. We like hard questions, and Jean-Louis, as you've seen, is capable to answer any questions. let's let's move on.
We'll see.
So you talked a lot about BTO, but today the material of choice is not BTO for modulators, because you mentioned that the market is already there, and
Yeah,
it's more lithium niobate today.
yeah.
So this is a reference material. So what makes BTO different?
Okay, let's first of all, let's comment on lithium niobate. Lithium niobate is a candidate who has Pockle effect. Okay, this is nice. Okay, but and it's available. You can buy it. Okay. For example, Soitec, yes, again, Soitec is selling a 6-inch wafer, silicon wafer with already lithium niobate thin films on it. This is not thin film, this is bounded wafer. And you're right, the BTO is not the material of choice. Why? Because there is no source of BTO. Either you build yourself or you make yourself the thin films BTO with the learning curve necessary to do that. Okay, and this is to bring that gap that we developed the ROSI to, is to let the community available with this new material. Thus, lithium niobate is nice material. However, the Pockle effect, if we take numbers for the Pockle effect, is 30. Okay, with BTO, it has been demonstrated in thin films that the Pockle effect is 1,000. Okay, what it means? It means that this is the ratio of size of your peak circuit. Thus, the BTO with this high Pockle effect has the possibility to have smaller size peak circuit. Why quantum computing is using BTO instead of LNO? This is due to that lower size peak circuit, you will have less losses, thus less error, and the possibility to have to build your quantum computer. Okay, thus
Mhm.
this is first thing. Second things, lithium niobate is, you should hear lithium. Lithium is a material which can never enter into CMOS fab. Okay. Thus, lithium is polluting a machine. A machine who see lithium cannot be used for standard CMOS thing. While barium or titanium is compatible with that. Already now, you have some big company like Global Foundries who are able to make circuit based on BTO on silicon. Okay,
Yeah, very
thus
interesting.
this is this. Okay.
But today,
Also, it what?
BTO is not yet everywhere. So what are the hard problems to solve with
Okay.
BTO?
The hard problem to solve is simple: chicken and egg. Okay. Everyone want to have egg to make good omelette. Okay. But before asking to buy a chicken, you need to have egg. And if no one is able to provide eggs, no one is able to make omelets, and no one can say, okay, I bet on that and I buy the chicken. And this is the gap
So
we are going to.
the chicken is called
Yeah,
Rosie in your
chicken is the
example.
rosy, the egg are the BTO on silicon, okay, good BTO, and the omelette is probably most of the audience here are making omelette. This is the big circuit with the good function and so on. After there is the customer, huh? Okay, who eat the omelette, okay, they need to be
So,
happy with that, okay, and the
so
bridge
in
needs to
fact,
be, oh yeah.
if I summarize, you need to have the BTO recipe to sell machines or machines to build the BTO recipe. So this is a chicken and egg effect, in fact.
This is
And
the chicken and
mm,
egg effect. If I
mm.
don't manage the epitaxy by myself to put into the machine to demonstrate that the material is good in terms of material properties after the throughput, after the return on investment and so on, no one will use that. Okay.
Mm.
This is
That's
why
why.
we build the Phoebe. Phoebe
That's
is
why.
a platform for making sample. Thus, the capex, I pay the capex. The only
Mm.
people want the people who will work with us with the Phoebe will use come on, the material or work with us in a closed loop way, or okay, just to improve or to evaluate the material. I don't say that LNO will disappear. Okay, I don't say that. Okay, but at least this is a novel material compatible, and it exists in 300 millimeter. Okay, this is not 6 inch. LNO right now, the biggest the LNO is built. You build a crystal size is no more than 6 inch. You slice it and you put this slice on silicon, or you buy this and you integrate. Okay. In this case, with the BTO, the promise is to grow directly BTO on 300 millimeter. This is the reason why we move 300 millimeter. We know that PIC industry is at mostly 6 inch or 200 millimeter. But if we want PIC industry become real, we need to prepare the future where the need will explode and the PIC industry will move uh, to 300 millimeter fab. Maybe not today, maybe not tomorrow, but at least we need to be prepared. And this is the key for a technology. We need to see the future.
We have a first question from the audience coming from Paul Irvins from the Latvian Competence Center. And he's asking about what are the most crazy microchip designs or applications that could be done with the equipment. And if I translate that, are there other applications than photonics, maybe in standard semiconductor?
Yes, yes. In fact, there is no today functional oxides, crystalline functional oxide in the industry. However, the ferroelectric properties or ferromagnetic properties of this bring a new kind of material. I will only say one. Okay, if you grow barium titanium oxide thin enough on a conductive oxide like strontium ruthenium oxide, what you build is a capacitor with low voltage and so on. And this is the possibility to have non-volatile memory directly on your CMOS.
Mm.
Next generation let's say circuit for computing the intelligent artificial intelligent computing will use such kind of things. Okay, thus this is one example of what can be done with other properties for the electronics, for example.
I think there's one company, right, working on that. Is there one company already working on this topic? Jean-Louis, can you hear me?
Yes, yes. This is right now. This is TRL4. Okay.
Yeah, that's
Now
very
we need
early
to move
stage. Okay.
forward. Everyone has worked on this and so on using STO, substrate and so on.
Mm.
But now we are giving the chance to grow this to a technology 300 millimeter, which is compatible with big fab.
So there's another challenge that you mentioned when we prepared this presentation. You mentioned that there's a characterization gap,
Yes.
which is absolutely mandatory. So can you elaborate a little bit on what is missing and what you will need to maybe accelerate your development?
Yes. Again, I will come back to the 3.5 semiconductor. When you are, this is an old industry or young industry, I don't know exactly, 30 years old and so on. But when you are making an epitaxy, okay, on wafer, you are able to really determine the key parameters, structural parameters, who will ensure that your device will work. For this oxide material, it's not possible. There is no now way to have access to, for example, the Pockels coefficient or the polarization coefficient without making a device. And this is the gap. Okay, this is for the characterization point of view. That's if we move for if we go for mass production, we don't need to break one wafer every two just
Mm.
to verify that the recipe is still constant. And this is one way I bring to the community. Is there any way to have access to the optical properties of these materials and to ensure that we will have a stable, let's say, Pockle effect.
Mm. Right. So
This is
yeah,
uh,
that the call is
structure.
open.
Yeah, the code is
The
open.
call is open for partnerships. So
Yeah, yeah,
basically today basically your objective is really to open the door to future partnerships, right?
exactly, exactly. A
Mm.
partnership is this. I will never be able to demonstrate a peak circuit. I'm only able to grow a material with some structural properties. Okay, but after that, I need to learn what structural property gives come on, this device working well or better,
Mm.
and so on. This
Mm.
is why this is a kind of partnership at the beginning.
Okay. So let's talk a little bit, let's take one step back and let's talk more about the business situation in the world at the moment. You are a European equipment maker.
Yeah,
We have seen that ASML is, for example, one of the indispensability in Europe for it's part of the value chain. There's a really very strong position of ASML here, but they're also facing some challenges. So, are you, Ribert, facing also some challenges between the US and China economic war or other topics, other problems?
exact. This is really a big problem for us. Okay, thus since the war between US and China, US companies say, okay, we don't want to have any products from US going to China. Okay, that's what to do because we are a system maker. We are not baking everything, every component. Thus we have tried to move to integrate all the components, only European components on our machine. Okay, just to skip the risk to have US saying no, you cannot sell these tools. Okay, for example, if you want to sell a tools to Huawei, it's difficult. Okay, this is
Mm.
first thing. Second things, with the war between US and China for the technology, okay, China invest a lot of money in 335 semiconductors. Okay, right now they double within this last 5 years. They double the productivity, the worldwide production of 3.5 semiconductors. They buy tens of MB 6000, for example, just to make their own chip for their own consumption, and maybe in the future to put those components into the worldwide. Why? Come on. In US also is doing so. Okay, thus they have already a big 3.5 industry. Okay, where they control the full chain, not really the full chain, but at least from the epitaxy to the device. In Europe, it's really explode. Okay, we don't have this. Pico Giga was a AP wafer, AP house, die in 2004. Now, if you want to buy AP layers and so on in large volume, let's say, you need to ask US or you need to ask China. And this is not really satisfactory because if you are far from production, you are far from the problem, and your machine, you cannot make it progress. Okay.
And are there any, in this 3.5 value chain, are there any issues with the supply chain? Because this is also one of the
Yes, it
key
can. It
aspects.
yes. Right now, with the explosion of AI, okay, does everyone want to have indium phosphide substrate, which is the raw material? On top of it, you grow your structure. And when you look a company like Sumitomo, who are delivering maybe 40% of the total indium phosphide, okay, material, US people, US company bought all the production since 2030. That's
Until 2030, all the
until
production from
20,
US company.
all the production will go to US company. China has developed its own way of growing this indium phosphide and so on. Thus they still sell those wafers to Europe. Okay, but a day they can say, oh no, we will stop it and you will
Mm.
buy our chip and not our
Yeah.
substrate. Okay, this is the danger. Of course, we have in Europe still some capability to grow gallium arsenide, indium arsenide with company like I don't remember Wacker Group or Siltronic and so on. But I think this is something we need to check. And there is also the raw material like indium, raw gallium, and so on.
Mm.
Thus, this is mining issue. We have champion like champion in Belgium like Umicore and so on, but I don't know if they really produce the indium and so on. Okay, we
Mm.
need to open new mine, huh?
I I read very recently we know that there is in France, I think, a company called Impact, which is
Yeah.
selling indium phosphide wafers,
Yes.
and they have been set on the blacklist from the Chinese government so that they cannot purchase anymore sourcing material from China. So
Okay.
this is one way where we see that the retaliation from the Chinese industry, from the Chinese yeah, business to the European one. So there's really always a way to the lower you are on the value chain, the lower you control the value chain, the more you have leverage actually.
Yeah. Yeah.
The value is very high, so this is something which is really a problem because the value is when you are at the highest point in the value chain, but the dependence on the supply chain is much stronger.
Mm.
All right. Yeah, we still have a few minutes. So, who are your competitors today? Who are your main competitors?
Yeah. Thus, now our competitors are system maker. Okay,
Mm,
like MB system maker. We have there is one which is big because they are a part of a big group. Okay, this is Vico. Okay,
mhm,
where they developed on the 3.5 market mass production machines and on oxide machine. They follow us, in fact, in developing a kind of rosy machine, not on the not really the same way as us, but anyway. And we have also a small company called DCA in the north of Europe. Okay, this in the north of Europe. DCA was a company really dedicated for the oxide growth. Okay, because they at the early beginning they built one machine and so on. But to be honest, right now is those machine has been bought by big name in the field of BTO, like PsiQuantum, Louis Phase, and so on. But this is not industrial tools. Okay, they never they they they, they are still far from R&D tools to jump into mass production tools. What we have done in the end of the 90s with the 3.5.
mhm, I see.
Okay.
While you were answering, I launched a poll for the audience. If you want to be connected to our speaker today, Jean-Louis, I will be happy to make the connection. If you
Okay.
want to be connected to your CHIPS Competence Center or to Access, don't hesitate
Okay.
to reach out here. So, Jean-Louis, today you mentioned that you're looking for partnerships.
Yeah.
So, what is the timing for you to build those partnerships, to have this?
Now, now we
Now
are
is a good time.
now is the good time. We have our first partnership, which is under construction. Of course, bringing different groups and so on. We ask funding from the Europe and so on. Thus, we are part of the Europe as the AP house, let's say, just to grow the materials. The first topics will be on, let's say, next generation electronics. What I say, okay, just working with Taiwan, and we are building also another strategic partnership for around the let's say the photonic. I cannot
right.
disclose yet, but I'd say a program will be deposited in October.
Okay, very
But
good. So
it's the good timing. Okay, I I already have basic recipe for the STU on silicon and so on with the Denmark, even if the sampling is slow. Okay, I cannot come promise to deliver 25 wafers, for example, only one or
mhm.
two, just to evaluate the technology and so on. But this is really the good timing to include our Phoebe capability to serve the different program with this novel material. And in the Phoebe, as you can see, we have two machines around the platform. Thus, we have one machine which will be completely dedicated for the BTO, STO on silicon, while the other will be equipped with some exotic materials like conductive oxide and so on. Okay, just to make exploratory work. Okay, but thus I'm looking for partnerships and building programs or only sell the wafer.
Mm. Okay, very good. That's clear, very clear. Thank you very much, Jean-Loup, for your time today. It was really an in-depth discussion into this area. I'm going to share again. Yeah, I'm sharing already my screen. So yeah, just to share my contact details if anyone wants to reach out after this meeting. So Jean-Louis, again, thank you very much for your time. So this session is recorded. It will be made available on our YouTube channel, and the next session. So there will be no session in August. The next one will be in the end of September, and so keep in touch to make sure that you won't miss it. Thank you again, Jean-Louis, and have a
Thank you very much,
great day.
everybody. Okay, thank you.
Bye-bye.
Don't hesitate to contact me. Okay,
Bye-bye.
bye bye.
Thank you.
Ciao.